In this video, we're going to take a look at the ideas from curve sketching, use them to try to solve problems that are optimization problems, right? So when we think about optimization problems, we're thinking about what is the optimal solution? What's the best solution? And in real-world kinds of applications, the best of something is often either the most or the least of something, right? So if you're in a business, you're looking for the most profit or the lowest, the cheapest expense, right? You might be trying to fence in the largest area of yard or use the smallest amount of fencing, right? And so that's what we're going to look at is optimization problems. So as we look at finding the maximum or minimum values, those are our optimal values. And so some general guidelines that we might use is we might first want to identify all given quantities and all quantities to be determined. If it's possible, make a sketch. So I will make a sketch on the vast majority of problems that I do when I'm trying to solve an optimization problem. We want to write a primary equation for the quantity that is to be maximized or minimized. Right? So what is it that we're actually trying to accomplish? What are we trying to maximize or minimize? We want to then reduce that primary equation to one having a single independent variable. In order to do that, we might have to come up with some secondary equations that relate the independent variables. So that we might find these secondary equations so we can rewrite our initial problem, our primary equation, as an equation having a single independent variable. And then we want to determine the feasible domain of the primary equation. So when we think about feasible domain, we just want to know what values does this problem make sense. Things outside of that we don't have to consider. So if we're talking about lengths, we typically don't have to worry about negative lengths. If we're talking about time, we're often not thinking about negative time, although it depends on the situation. Sometimes people will talk about this an amount of time previously, but you just want to think about your feasible domain, and then we determine that desired max or min by finding critical numbers, and then we will use either the first or second derivative test. I will tend to use the first derivative test, but you can use the second derivative test as well. It just sort of depends. You have some freedom there. All right, so let's look at our first example. So here we have a three-sided fence is to be built next to a straight section of river, which forms the fourth side of the rectangular region. The enclosed area is to equal 1,800 square feet. We want to find the minimum perimeter and the dimensions of the corresponding enclosure. Right. And here when I say the perimeter, what I really mean is the perimeter fencing. And so I just want to know what's the smallest amount of fence that we will have to use. All right, so let's see if we can draw a picture that represents the situation, not just any picture. So we have this river. Next to this river, so this river is going to be one side of our rectangular region. So the fourth side of that rectangular region. So we have some fence up here, and here, and here. So we could call these two sides length x and this side length y. That's the picture of the setting. We also want to identify any given quantity. So we identified x, those are the sides that are adjacent to the river, and y is the side that's parallel to the river. We have the perimeter of fencing. It is going to be 2x plus y. That's the amount of fencing that we will need. We also have one other piece of information. We know that the area the enclosed area is 1,800 square feet. So our area, which is 1,800 square feet, how do you find the area of a rectangle? Well, the area of a rectangle is length times width. And so here we have x and y as the lengths and widths. And so we have this relationship between x and y. X times y is 1,800. So we could take that equation, we'll use that here in a moment. So the perimeter, what are we trying to do with the perimeter? We want to minimize this perimeter. So we're going to minimize that. When we look at it initially, so this is our primary equation. This primary equation has two separate independent variables. So how could we get rid of one of those? Well, that's where we're going to make use of this secondary equation that we've already identified. So we can say up here in the secondary equation, we could solve this for y. We could say y is 1,800 over x. So our perimeter equation can be rewritten as 2x plus 1,800 over x. 1,800 over x is the same thing as 1,800 times x to the negative first power. And then what are we going to do with this primary equation now? Well, we want to optimize it. We want to find the maximum or minimum. So we're going to try to find critical values. To find critical values, we need to take a derivative. So we'll take our derivative. Our derivative here, p prime, is going to be 2 minus 1,800 x to the negative 2. What are we going to do with that derivative? Well, let's set it equal to 0 so we can find these critical numbers. Uh, 1,800 over x squared is equal to 2. So 1,800 is equal to 2x squared. So 900 is equal to x squared. If we were to take the square root of both sides, we'll get x is equal to 30 or negative 30. Now, one thing I did jump over is I didn't consider my feasible domain. So what is our feasible domain? So what's going to be true of the x values? Well, those x values are lengths of fencing. So negative values will not make sense. A value of 0 doesn't really make sense. So if you have no fencing along that edge here, that doesn't really give you a rectangle. So really our value of x should be larger than 0. And so this is what we have as our critical value. Does that mean that that for sure is our solution? Well, not with certainty. So what I might do here quickly is I might do a quick sign chart. And so I'll go from 0 to 30, and from 30 on up to infinity. Just choose some value between 0 and 30 to plug into your first derivative. So let's just say 1. If we were to plug in 1 right here, we will have 2 minus 1,800, which is a negative value. Plug in something larger than 30. So, I don't know, you could pick like 10,000. If you picked something like 10,000, you would have 2 minus 1,800 over 10,000 squared. So this is going to be a number real close to 0. 2 minus something close to 0 is positive. So you'll be positive after that. So this tells us our function is decreasing, and then after that it's increasing. So right at 30, we must be at a minimum. So there's a minimum when x is equal to 30, and the units on that are, Well, the 1800 was in square feet, so this will just be in feet when x is 30. And what is the y value when x is 30? Well, our y value we set up here was 1800 divided by x. So 1800 divided by 30 will give us 60. And so we have a minimum. We minimize the amount of fencing needed when we make those two sides here equal to 30 and this side here equal to 60. What's the total amount of fence that's needed? Well, the total amount of fence that's needed is 120 feet of fencing. And that is our first optimization problem. Come on back for our next video when we will look at another optimization problem. We'll see you there.